Welcome to our yet another lecture on machine learning as part of Introduction to Data Science. In this lecture, we will be covering some more basic algorithms and some evaluation techniques for our machine learning algorithms. So let's begin. In the outline for today's lecture is we would be covering naive Bayes, which is a machine learning algorithm. Then we would be discussing logistic regression and some SVM as well. Then some random forests, and then at the end we would be covering evaluation techniques which would include precision, recall, accuracy, plus weighted loss, ROC, and arc and lift. If you remember from the last lecture, we categorized the machine learning into two types: supervised learning and unsupervised learning. In the supervised learning part, we discussed KNN or k-nearest neighbors, linear regression, and in the unsupervised learning part, we discussed clustering. There are some other unsupervised learning methods as well, which include factor analysis and topic models. In today's lecture, we will be covering some more supervised learning techniques, so we will start with the naive Bayes. So let's begin. So naive Bayes algorithm is based on the Bayes theorem, which we already covered in the statistical learning part of our course. Let's recall a bit of that. So we have probability of an event A given B, which is called conditional probability, which basically means that the probability of an event A given that B is true. And by Bayes theorem, this is equal to the probability of B given A times PA divided by PB. So in practice, we are more interested in dealing with events and data. So let's say our event is that I have a cold, which is, let's say, something that we have to decide about. And the data that we have is runny nose, watery eyes, and coughing. So we are interested to calculate the probability of cold given the data set, given these evidences. And we can use Bayes theorem for that. So Bayes theorem is basically diagnostic. Here is Venn diagrams of which represent different probabilities in the Bayes theorem. Here you can see the conditional probability, the joint probability, and the conditional probability after seeing the evidence, which is also called the posterior probability. So in this new formula for the Bayes theorem, which is exactly the same as the previous one, but instead of using A and B, now we are using E and D, the event E and their diagnostics or the evidence is D. In this case, PE is called the prior probability of E. It is what we know or think we know about E without any evidence, without looking at the data D. Then we have the conditional probability PD given E, which is the probability that this given data set is generated if the event E was there. Then so this is called the likelihood of D. Then we have PE given D, this part which we want to compute, which is the probability of E after observing the evidence D. So that's why because it's after the evidence, so this probability is called the posterior probability. And it's the answer we want, or the answer that we are looking for, and we want to choose the best answer. In a naive Bayes classifier, which is based on the Bayes theorem, we assume that we have an instance. Let's say it's a document D, and this document D has a set of features. Let's say it could be the number of words in the document and the frequency of certain words, and the size of the document, etc. And based on these features, we want to decide which class or which topic this document belongs to. So our data is the document, and the classes are probably the topic of the document or the subject of the document. So we want to find the most likely class that the document belongs to given its features. So the joint probability of the class and the features is given by this expression, which is the probability of feature 1, feature 2 up to feature k, and the class Cj. So we would have a joint probability for each class. Then, okay, the naive Bayes classifier is called naive because there is a key assumption that the features that are generated by the class Cj are independent of each other. So because of this independence assumption, we can express this joint probability as a product of individual probabilities. So you can first by probability theory you can separate these two into factors, converting this into conditional probability times the probability of the condition, and then you can convert this condition. You can factorize these conditional probabilities because they're assumed to be independent of each other. The features xi are, then that's why you can write them as a product. So based on this joint probability, we want to figure out the most likely class to classify the document, which is the class Cj, which maximizes this posterior probability. Now from naive Bayes we know that we have this formula which to express the theorem. The posterior probability is equal to the likelihood times the prior divided by the probability of the features. But to choose the best Cj, we can ignore this part, this denominator, because it's independent of Cj. It's the same for all the classes. So we can maximize the posterior probability by just maximizing this product, the product of prior and the likelihood. So we can finally pick the category Cj or the class Cj, which maximizes this expression. So that actually means that we can calculate this expression for each Cj, and for a given x, for a given xi, and then for that xi, for that set of features, we would decide that the best Cj is the one which gives us the maximum value for this expression. The data for naive Bayes, we need the data. We can use the data to find the best class, and for that we needed two pieces of information or two pieces of data. One is the prior probability of the class, and the other one is the conditional probability of feature given the class, which is also called the likelihood. So we just need these two terms for each class, for each Cj, and we can take the product of these two terms for each class and then determine the class as the best class, which gives us the maximum value among these products for all the classes. Okay, so to calculate these two values, these two probabilities, we can use the counts. For example, the probability of class Cj, irrespective of the data or irrespective of the evidence, is equal to the number of samples that belongs to class Cj, irrespective of their features, divided by the total number of samples. So that would give us the prior probability of class Cj. To determine the probability of evidence xi for the given class, we can calculate the number of samples that have both xi and Cj and divided by the number of samples that belongs to the class Cj. So in this manner, the training for naive Bayes is basically just counting the number of samples for each class and for each set of features. So, but the count data is only an approximation to those probabilities. So for instance, if we have access to infinite samples, infinite data, or all the population, then we can assume that these counts would give us exactly the probability. But since the samples that we have are only a subset of the population, so there is a bias involved, and we can use these counts as just an approximation. So this might be problematic. So that's why we can assume, we can expect that there would be some error. Another problem with the counts is that there could be a count of zero as well. So for example, there could be um, the number of samples belonging to a certain class could be zero, or the number of samples belonging to a certain class having certain features could be zero. So in that case, we can have the probability which is a number divided by zero, which should be undefined. So for that we can use Laplace smoothing, which means that we can add a certain alpha and beta to both the numerator and denominator, so that even if n1 or n2 are zeros, we would still get a non-zero number here. And this alpha and beta are small values, small constants, and this basically adds another layer of Bayesian inference and pushes this p towards a pair of alpha divided by beta. So, and these constraints can be set based on a prior knowledge, or they can be learned during the training phase. The good, the bad, and the ugly of neo-Bayes classifier are the good thing about neo-Bayes classifier is that it's simple, it's fast. Simple is only depends on the term frequency data for the classes, and it's one shot. There are no iterations, so you just have to go through the data only once to have all the counts. It's very well behaved numerically. The term weight depends only on the frequency of that term, and it's decoupled from other terms. It can work very well with sparse data where combinations of dependent terms are rare. The bad thing about naive-Bayes classifier is that it's subject to error and bias, specifically because the counts, the fraction of counts are not exactly equal to the actual probabilities, and in actual the term probabilities are not actually independent. So for example, in URL prefixes there might be dependencies among the features. It can't model patterns in the data, and typically it's not accurate as other methods. Okay, so moving on, we discuss another regression, another classification or machine learning algorithm, which is called logistic regression. If you remember, we made a distinction earlier between regression, which is predicting a real value, and classification, which is predicting a discrete value. So logistic regression is somewhere in between. So it's designed as a binary classifier, where the let's say the output is between zero and is either 0 or 1, but actually the outputs of a logistic regression is not the class 0 or 1, but the probability of a certain class, let's say the probability of class 1. So for example, if we want to build a classifier to diagnose a disease, then the output could be the probability of that disease, not the decision that whether this disease is there or not. So, but actually outputs the probability that the input instance is in the one class. The expression for logistic classifier is given by this formula. So it's the probability of x, which is equal to 1 divided by 1 plus exponent minus x times beta. So if you remember, this x times beta was our linear regression algorithm. So we just, so once we calculate the output of the linear regressor, you can just put it in this formula. So this just by adding another layer to our linear regressor, so that each output of a linear regressor would be converted to a probability between 0 and 1. So logistic regression is probably the most widely used general purpose classifier. It's very scalable and it can be very fast to train. It's used for spam filtering, it's used for news message classification, website classification, product classification, and most classification with large and sparse feature sets. The only caveat is that it can overfit on very sparse data, so it's often used with regularization. Logistic regression basically maps the regression value that is x beta in and because it's a regression value, so the range is between minus infinity and plus infinity. It's a real number, so it maps the real number to a range 0 and 1 using a logistic function, which is, so this function is, because of this logistic regression, the function is called logistic function, and here is the plot of the logistic function. So whatever the input is, the output is always a number between 0 and 1, a continuous. So it's a continuous function, outputs a continuous value, but it's a bounded value. So which means that the logistic function maps any value on the real line to a probability in the range of 0 and 1. So where this logistic function come from? So logistic function actually comes from naive Bayes, and it's actually a generalization of naive Bayes with binary features. The difference between a logistic regression and naive Bayes is that naive Bayes can have many more features, but logistic regression only have 2 features. It can model a naive Bayes classifier when the binary features are independent. So let's say we have Bayes rule for 2 classes, C and not C, and so this is how our Bayesian formula works. You can change this denominator to this um, by uh, by dividing this probability of the features to 2 parts: probability of the feature given conditional probability of the feature given class C, and probability of features given the class not C. Then divide both the numerator and denominator by the numerator. You get this formula, which now looks like it's becoming like the logistic function. So if now we have this, which is equivalent to the logistic function 1 divided by 1 plus exponent minus xb, which matches if this part is equal to this exponential term. And if we assume the feature independence, we can factorize this left hand side by taking the product of the individual probabilities. Also you can factorize the right hand side, and we can match the corresponding I in terms to define beta. So let's see at a summary of the logistic function, logistic regression. It has this form. It can model a naive Bayes formula with 2 classes after dividing through by one of them. So we divide the naive Bayes formula with 2 classes by dividing by one of them. So we have these ones here because of the division, and we have this exponential term. Logistic regression can always learn a naive Bayes model, but because it's more general, so logistic regression should do at least as well as naive Bayes, which means that the performance of logistic regression can be better than naive Bayes, and the least it could perform is as good as naive Bayes. But this may not be true if the logistic regression logistic model, because it overfits easily. So if it overfits, then the performance can be worse than naive Bayes because of the overfitting. But overfitting can be avoided by using L1 regularization. So logistic regression typically does better, though, because it can deal with dependencies between features, whereas naive Bayes cannot deal with dependencies between features. The training for logistic regression, we start with the collection of input values xi and corresponding output labels yi, which is a number either 0 or 1, and let pi be the predicted output on input xi. So pi is given by this logistic formula for the xi and given beta. Then we can calculate the accuracy on that certain input xi, which is given by this expression. And the logistic regression basically tries to maximize the sum of this accuracy, or the log of the sum of the log of accuracy. So this is our sum of accuracy. So the logistic regression during training would try to adjust this value beta such as to maximize this sum of accuracy or sum of log of accuracy. So to find the best beta, we can use gradient descent on the derivative of d on the derivative of this a. So if we calculate this gradient, this is our gradient now by putting the values of ai from here, and we want to find out the value which for this gradient which maximizes a, so that way you can equate it to 0. So let's see how these different terms behave in this gradient. So this value 2i yi minus 1 is a number either minus 1 or plus 1. So because when yi is plus 1, this number is plus 1, 2 minus 1. When yi is minus 1, this number is minus 1. So minus 2 minus 2 minus 1. Then the second part is a number between 0 and 0.25. So if pi is close to a central value, it would be the maximum 0.25. If it's far from the central value, it would be a smaller value which is around 0. The positive instances gets weight pi into 1 minus pi, because for positive instance this number would be plus 1, while the negative instance get the weight minus pi into 1 minus pi, because this number would become minus 1. The weight is largest for the inputs with p around approximately equal to 0.5, which are near the decision boundary. And here you can see how we plot p into 1 minus p. The training of logistic regression can be done using stochastic gradient descent, which is a very efficient way to train the logistic models, where we keep updating the models with gradient from small blocks or mini batches of input data. One challenge with the training on power law data is, which most of the practical data is, that the terms in the gradient can have very different strengths because of the power law distribution. This means that some gradient terms are thousands of times larger than the others, but the beta coefficients are about the same. It shouldn't change much, so that's why if this imbalance makes training very slow, which means we would need more steps to reach an optimal value of beta. There is a recent method which is called error grade, which is adaptive gradient descent, which normalizes each coordinate of gradient by the historical or from previous iterations magnitude of that coordinate. So the error grade technique often leads to extremely efficient training, and on large data sets it's not unusual for a model to converge in less than one pass over the data set. So even we can get to the best beta, to the best parameters of the model by not using all the data set even once. So this efficiency of the logistic regression model even is more than the naive Bayes, because in the naive Bayes we need at least one pass over the whole data sets. Okay, next we will discuss a brief about support vector machines. A support vector machine is a classifier that tries to maximize the margin between training data and the classification boundary, which is the plane defined by x beta equal to 0. So this is our classification boundary. So all the samples on one side of the classification boundary belongs to one class, on the other side belongs to the other class. But we also draw these extra two lines which are called the margins, and the SVM classifier tries to maximize these margins as far from the boundary as possible, so that there are no errors in the test data or less errors in the test data. So let's say we have these test samples which are beyond these boundaries but still can be easily classified using this central boundary. The SVM can be trained using stochastic gradient descent. You can recall that the logistic gradient was, and this time assuming that the class level is either -1 or +1. So this was our gradient for the logistic regression. We can use this concept now to define a gradient for SVM by changing pi to xi beta, and that is that if pi yi is less than 1, then we would use yi xy is the accuracy, and if it's not less than 1, then we would use 0. This expression basically tests whether the point is in the margin, and if so, it adds it with sign yi, and it ignores other points. So if the point is not in the margin, it would ignore that point. It would not use that point to change the parameters or to train the model. And if it's in the margin, then it would use that point to update the parameters of the model. These both methods weight points near the middle or near the margin with the sign yi. Our next classification algorithm is called decision trees. In decision trees, we walk from root to a class level leaf, and each node a branch based on the value of some feature. So in this case, we actually partition the data that we have into subsets based on some features, and we keep on partitioning the data till we reach a subset which where all the samples belong to a pure class. So for example, let's say we have a data set, we use a features patterns. Let's say these features has 3 different values: none, some, and full. We divide the data into 3 subsets, and let's say the first subset, where the pattern feature is none, all belongs to the class F. In the feature with some value some, all belongs to class true or T, and all the samples with the feature value equal to full, patterns feature equal to value to full, they belong to different classes. They all contains different classes. So then we can use another feature to further partition the data set. We keep on doing this until we reach our leaf nodes, where the leaf node basically contains a pure class. We can do that till all the samples are assigned a class value based on when they reach a leaf node, or if that's not possible, we can do that by assigning a maximum depth of the tree, and once we reach the maximum depth, then we can assign the class to further assign a class or label based on the majority vote. Okay, in the decision tree learning, if there are k features, and the decision tree might have up to 2 raised to power k nodes, and this is usually much too big in practice. So we want to find an efficient implementation of this decision tree algorithm, which means we need more smaller trees. The problem with larger trees are twofolds. Once on one side it's too complex, it takes a lot of time. On the other side, it usually overfits on the data. So for to have an efficient tree, we can use a greedy manner by recursively choosing a best split feature at each node. Okay, so the best split feature, by best split feature we mean that we want to choose an attribute and a feature which is then when used to divide the data into subsets, creates the most division based on the classes, which means ideally all positive or all negative. So let's see 2 examples. Let's say we use features patterns in the first example and use feature type in the second example. We have this input data where half the samples belong to the green class and half of the samples belong to the red class. If you use patterns, then you can see on one leaf we have a pure class, on the other leaf we have a pure class, in the third leaf we don't have a pure class, but where some samples belong to one class and that the rest of the samples belong to the other class. On the other hand, if we use feature type, then in all the nodes, under all nodes, the subsets belongs to two different classes, and they have this equal probability belonging to each class. So in this, so you can see that it's better to divide on patterns as compared to type. So mathematically we can use entropy for that to choose the best feature for the split. Entropy is defined at each node based on the class breakdown. Let's say we have pi, which is the fraction of examples in the class I, and pif is the fraction of elements with features f that lies in the class I. Then pi not f are the fraction of elements without feature f that lie in class I. And finally we have p of pf and p not f, the fraction of nodes with respect with and without the feature f, irrespective of the classes. We can use these fractions to calculate entropy. So before the split, this is our entropy, which is pi times log of pi and sum over I from 1 to m, where I is the class label, and there are 5 classes, m classes, sorry. Uh, um, uh, you can see here log of pi is a number between 0 and 1, so log of pi is always a negative number, so the entropy would be a positive number because it's multiplied by this minus sign twice. After split by the feature f, this is our new entropy, which is we calculate the entropy based on when the fractions of samples belonging having feature f and the fractions of sample belonging to I not having feature f. So this is called the entropy after the split. So if there is a change in the entropy after the split, if the new entropy after the split is less than the previous entropy, we would get some information gain. This information gain is basically represented by the difference between these two entropies. So we would use the split, the feature f, that would give us more information gain, which means that if the entropy is decreased after the after after the split, then this would be a higher number, and we would use that split or that feature to split. So let's see an example. Here we have some input data with the 3 different classes A, B, and C. If we divide by a feature, let's say we divide by the feature patterns. Now on both sides we have almost the same fraction of classes, and the probability of classes are still remain the same. So if we calculate the entropy before the split, it's equal to 1.5 bits. If you calculate the entropy after the split, it's still 1.5 bits. You can verify it from here as well that the probability or the fractions of the classes did not change after the split in on both sides. If we split it by type feature, then you can see here that on the right hand side after the split we have 2 classes with probability 0.5 and 0.5, and on the left hand side we have 2 classes with probability 0.5 and 0.5. On the left hand side the probability of class B is 0, on the right hand side the probability of class C is 0. Before the split the entropy was 1.5 bits, and after the split the entropy is 1 bit, so we have a gain of 0.5 bits. So this tells us that this information difference between information gain tells us that it's better to divide the data into partitions by feature type feature rather than patterns feature. Okay, so at each node we choose the feature f, which maximizes the information gain, and then this tends to produce mixture of classes at each node that are more and more pure as you go down the tree. So with each split, there would be still a mixture of classes on the node, but they would become more and more pure as we go down the tree. If a node has examples that all belongs to class C, we make it a leaf node and output C. Otherwise, when we hit the depth limit, we output the most popular class at that node. And if we are not at the depth node limit, we can keep on partitioning the data, the remaining data based on the same feature or other features. Okay. Next are a series of algorithms which are called ensemble methods. They are like crowdsourced machine learning algorithms. In ensemble methods, we take a collection of simple or weak learners and we combine their results to make a single better learner. The types of ensemble methods are Bayesian. In Bayesian, we train learners in parallel on different samples of the data and then combine by voting, which gives us a discrete output, or by averaging, which gives us a continuous output. So in Bayesian, let's say we have a training data set. We can divide the training data set into subsets and then train a different model, a different learner on each subset, and then at the end combine their results by voting if it's a classification problem, or by averaging if it's a regression problem. Another ensemble learning method is called staking, which we will combine model outputs using a second stage learner like linear regression. So instead of just voting or averaging, we use another linear regression learner at the end of Bayesian, and that's called staking. The third method is called boosting, where we train learners on the filtered output of other learners. So boosting works in series as compared to Bayesian. So that is that you train a learner based on some input data, and then the error of that learner, the error that you have in that learner and the data set, some new or the previous data set is used to train another learner. So we keep on doing that till we get a better model at the end. Okay, we would cover one ensemble learning method which is called random forests. As the name suggests, it's an ensemble learning method which use decision trees as the base learners. So in random forest, we grow K trees on data sets sampled from the original data set with replacement, which is called bootstrap sampling. Here let me tell you a little bit about bootstrapping. In bootstrapping, we select one sample at a time from a data set randomly, so that each sample has a probability of 1 divided by n of choosing, and then we replace that sample in the data set. So there is a chance, there is still a 1 divided by n probability associated with each sample, even after it's chosen. So at the end, when you finish this bootstrap sampling, there will be samples which are redundant in this selected data set. In this method, we actually choose a subset of the data which includes almost 63% of the samples. We can use those samples for training and the rest of the samples for testing or adjusting the parameters. And let's say we have p number of features then. Okay, we draw k bootstrap samples of size n, which means we perform this bootstrapping k times, and each time we get n samples. Then we grow each decision tree, those k decision trees, by selecting a random set of m out of p features. So for each decision trees, instead of using all the features, we only use a subset of features at each node and choose the best feature to split on. Then we aggregate the predictions of the trees using most popular vote to produce the final class. Typically, the number m to choose the subset of features p, it might be the square root of p, but it can even be smaller. The principles of random forest there are that we want to take a vote between different learners, so we don't want the models to be too similar. These two criteria ensure diversity in the individual trees, and it actually ensures that the classifiers are not biased on the input data, and they do not overfit. We draw k bootstrap samples of size n, and each tree is trained on a different data. And we grow a decision tree by selecting a random set of m out of p features at each node and choosing the best feature to split on. So in this manner, like we increase the diversity as much as possible by ensuring that the sample that are used to train the trees, the base classifiers are independent from each other, and also the features that are used are also selected randomly and independently of each other. The corresponding nodes in different trees usually cannot use the same features to split. Random forests are very popular in practice. It's probably the most popular classifier for dense data, where the dense data is the one which has a few thousand features. It's easy to implement. We can train a lot of trees, and it's a good match for the map reduce. Random forest parallelizes easily, but not necessarily efficiently. The bad thing about random forest is that it's not quite state of the art. It does not give quite state of the art accuracy. There are boosted trees which generally do better, or deep neural networks. It needs many passes over the data, at least the maximum depth of the tree, which is much less than the boosted trees. And it's easy to overfit, and it's hard to balance accuracy over fit trade-off. So this is all about some machine learning algorithms that we wanted to cover during this lecture. In the next part of the lecture, we would cover the evaluation methods for different models, learners, and classifiers, and for different machine learning algorithms. So stay tuned for the next lecture. This is me signing off. Thank you very much.